Hello, my name is Agam Herba and I'm a PhD student at the University of Massachusetts in Amherst. Today, I'll be talking about some of the work that my colleagues and I are doing on using vision transformers to improve road quality predictions from medium resolution satellite imagery. Efficient road infrastructure is vital for any economy's economic development, particularly in the global south, where it is of paramount importance to connect rural areas to urban centers in order to facilitate agricultural growth and overall economic well-being. Given that a lot of countries in the global south depend on agriculture to facilitate, to fund their annual GDP, it is of paramount importance to make sure that these roads are in a proper condition. However, monitoring infrastructure is very expensive, especially for these governments that depend on donor funds to fund most of their budgets. Existing methods, if used, also do not account for all roads, more especially those in rural areas. However, satellite data offers a cheap alternative that is globally applicable. Now, we've seen an increase in the number of operating satellites that have been launched in the last few years. This means that we have high-resolution satellite imagery with frequent reviews, and in that way, we are able to observe individual road segments across time and space. So this brings us to the big question: how well can we predict the quality of a given road from medium-resolution satellite imagery? In order to achieve this, we use two data sets: the International Roughness Index and satellite imagery. I'll start with the first data set. The International Roughness Index is a measure of road's bumpiness. In other words, the less bumpy the road is, the better the road quality. On the other hand, if the road is more bumpy, then IRI values are going to be high, meaning that it is of poor quality. Our study area is the Republic of Kenya, and we used a total of 57 roads covering 7,000 kilometers. However, in order to align with the existing satellite imagery that we had to select only measurements taken between June 2015 and June 2016. Furthermore, IRI measurements are recorded at 10 meters interval with a corresponding longitude and latitude. However, given that we had medium satellite imagery, we decided to downsample these IRI measurements to intervals of 50 meters in order to avoid image patches from overlapping and causing overfitting in our models. For satellite imagery, we use two data sources: Planet Lab, which has imagery existing at 3.8 meters per pixel in rural areas and 3.0 meters per pixel in urban centers, as well as Google Earth Pro at around 1.6 meters per pixel. Now, we had to make a trade-off between spatial resolution and frequency. Here's what I mean. Google Earth Pro is less frequent. In other words, you can have one image existing for some region for a span of like 1 week to 6 months or even 1 year. On the other hand, Planet Lab imagery exists consistently every day from around late 2015. However, it has low resolution, so it's a choice of should we use low resolution but more temporal available satellite imagery, or high resolution but less temporal available satellite imagery. The key takeaway is that we experimented with different resolutions, visibilities, and qualities in order to understand what trade-offs have to be made in order to make predictions. So, we have our IRI measures, we have satellite imagery. What next is how can we define a prediction problem? So, IRI measurements are made as continuous values. And the first step is to discretize them into classes. For example, we can set a defined threshold, let's say 10 meters per kilometer, and anything below 10 meters per kilometer is defined as good, and anything above that is defined as bad. Now, given that each IRI measurement has a corresponding longitude and latitude, we are able to extract an image patch over that area, thereby creating an image label data pair, which we can use if we have a lot of these to train a suite of computer vision models, for example, CNNs or vision transformers, in order to predict a label given an image patch. For evaluation, we ran a set of experiments, including the traditional train test split from the same data distribution, as well as training on one set of full roads and testing on another set of full roads that are not in the training data, or what we call the held out experiment. We also experimented with different image resolutions as well as varying data sources. Now, our major interest is on our held out case because this is what exists in the is what we expect in the developing regions. In other words, we might have images in one country and we want to influence in another country that there's no data. So we train a model on regions where there's data, and then we do inference on regions where there's limited to no data. For the choice of computer vision, we selected two, the vision transformers as well as the traditional convolutional networks. For vision transformers, we selected three models. One, the vanilla vision transformer, the Convenex, which is a hybrid of convolutional networks and transformers, as well as the data efficient transformers. The advantage with vision transformers is that they are well able to generalize across different domains. Again, this covers our need of training in regions where there's data and inference on regions where there's little to no data. For the baseline, we use the ResNet, which is a convolutional network, and much as we acknowledge that there could potentially be a risk of overfitting, but with different tricks here and there and improving the architecture, we could actually get good results. For both vision transformers and CNNs, we use those that have been trained on ImageNet. We aggressively refined them with low resolution satellite data, which is Sentinel at 10 meters per pixel, but we did not have any substantial improvements, and as such, we decided not to invest in more computational power and time in order to improve the performance. In order to evaluate the performance of our models, we based performances on area under receiver operating curve, which basically represents the model's ability to distinguish between positive and negative classes, with the value of 1 indicating a perfect discrimination and 0.5 indicating no better than random guessing by the model. A few points taken out from these points. We see that both CNNs and vision transformers perform excellent on high-resolution satellite imagery, and that is Google Earth Pro, as is expected. And this is true for both binary class classification as well as 5-class classification. Additionally, we see that vision transformers outperform ResNets, though it's by a small margin. Well, 0.3 is not a small margin as per se. The key takeaway is that both vision models and and CNNs perform better when spatial resolution is high, as would be expected from data from the same distribution. However, our key goal is to evaluate how this model will perform if they were exposed to data that is not from the same distribution, or what you might call held out case. So based on these performance actually flips, we see that when we train on one set of full roads and evaluate on another set of full roads, performance actually flips, with models trained on PlanetLab performing better than those trained on Google Earth Pro. However, this condition occurs only when we have enough training, enough data points for training. So performance still is relatively good, with vision transformers performing better than ResNet across binary and 5-class classification. But the important point to note for this slide is that when spatial resolution is low, but we have enough data points, then we are still able to get better performances with vision transformers. The final experiment we did was trying to evaluate how much data we would need in order to get relatively good results. And we were able to get pretty much similar results with as few as 10% of the data points, which is on average 3 rods. So what are the major takeaways from this paper or this work that I've just talked about? One, convolutional networks, neural networks, as expected, perform well on high-resolution imagery, but fail when quality degrades. Now, from the structure of CNNs, this makes sense because CNNs perform spatial hierarchical processing. In other words, they extract information from the image in hierarchies. Now, this means that if an image already has limited details, then that gets lost in transition. Now, given an example of a satellite image, if it's low resolution and the road occupies a small percentage of the imagery, then that information is going to get lost during the information extraction process. On the other hand, vision transformers perform well even when spatial resolution is low, but then you still need lots of training data. Again, this performance makes sense with vision transformers, specifically for the structure of vision transformers, that is self-attention mechanism that is able to capture global relationships independent of any image resolution. That means that if a rod exists on a small section of a satellite imagery, however low it is, it can still be associated with the label. Finally, we established that overall it doesn't depend on low resolution or high resolution, but data efficient transformers on average outperform CNNs when resolution is low and data is sparse. So we took all these lessons we learned and we applied them to a real world case study, and we wanted to understand how I wanted to see whether better roads usually lead to an increase in asset wealth. To that, we randomly selected 85 small towns in Kenya and then extracted road patches in a 2-kilometer radius. Then we used the best performing model to perform inference, and then we calculated the difference in the percentage of roads predicted as good between 2016 and 2020. We compared this against change in the annual estimated household asset wealth across the same duration, and we observed a small but positive correlation between the two variables. Now, it should be noted that road quality is not a clear indicator of economic of change in wealth of an economy. However, what you are trying to prove or what we are trying to show is that road quality can be used as one of the major indicators for economic well-being of any nation. Future work will involve applying more to case studies. We are currently working on understanding the impact of large-scale infrastructure investments on peace and economic well-being in the Eastern Democratic Republic of Congo. Additionally, we are working on producing inference maps of all roads across the African continent, as well as continuously improving the performance of vision transformers on relatively low but more publicly available satellite imagery, that is Landsat and Sentinel. Additionally, we are gathering more IRVs for countries across different kinetic regions, economies, in order to have better generalization in these models. If you have any questions, please reach out and you can scan the QR code to read the paper.